Hello everyone. In this video I am going to talk about greedy algorithms. Greedy algorithms is another famous problem solving technique in algorithm design, um, which has a very interesting properties. Although it actually, those properties makes it completely different than dynamic programming, but yet there is a close relationship between dynamic programming and greedy algorithms. So in dynamic programming, basically the idea was that we do the complete search, we do the exhaustive search over all possible solutions, but whenever we see some repeated sub-problems, we, by storing the answer for those sub-problems and reusing them, we avoid the exponential time complexity. But still, it's just like you are doing the complete search, you are doing the exhaustive search over the search space of all the answers, right? So in greedy algorithm, the difference is that we always know that one choice is going to end up to the optimal answer. So by knowing this fact, we don't need to do the exhaustive search. So this is the whole idea. With the greedy algorithm, very similar to the dynamic programming algorithm, is applied over the optimization problem. And the whole idea is that in dynamic programming, we do the exhaustive search, we check all the possible choices because we have to find the optimal answer. But for some problems, we can find some property, some specific property that allows us to just always choose one action. And if you have, for example, if you have a couple of actions to choose, the problem has this property that you can just choose one option, one action, and it always, you know that it always ends up to the optimal answer. So you don't need to check all the possible actions at each situation. So I think the best way to explain it is through an example. One of the famous examples of greedy algorithm is the optimal coin changing with this specific denominations that, for example, like the Canadian coin system or American coin system. So let's actually just talk about the Canadian coin system. That we have toonies, loonies, 25-cent quarters, right? 10 cents, 5 cent, and assume that we have a penny as well. The problem, we have seen the problem in the dynamic programming discussion. The problem is that you have some amount of money, you wanted to change it using this set of coins. Okay, so if I'm going to do it like the way that we did for dynamic programming, so let me, okay, we are in edit mode. You started from having, actually, for example, you are going to change X amount of money, right? You started having the X amount and you are going to actually change it, right? So in the dynamic programming case, you would do the complete search. You would actually say that what would happen if I choose for example, a toonie. Just assume that X is greater than $2 so that I can choose, take toonie. If not, you would actually just start it from the largest one, which is smaller than X. What would happen if I choose $2? So the amount will be X minus $2, right? What would happen? What would be the optimal solution? What would be the best answer that I can get if I choose a $1 loonie? So this is going to be X minus 1. What would happen if I choose a quarter? So let's just write it like this. And what would happen if I I started to actually just minus 10 cent, minus 5 cent, and minus just 1 cent. Okay, you find the optimal answer in all of these different branches, right? And the optimal answer for x, for changing x, is going to be the minimum among all of these branches. And you actually just expand all of these, right, with all the options that you have. This is the complete search, and this is what the dynamic programming will do. The only actually a smart thing that the dynamic programming will do is that if it finds some repetition between subproblems, by storing them and reusing them, it avoids that repetition and makes the time complexity polynomial. Okay, so what if I tell you that the optimal answer that you can get from all of these branches, if you actually just, what if I tell you that, let me actually use a different color. If you choose this branch and find the optimal answer in this branch, whatever you find in other branches cannot be better than this branch. So if you know that, definitely you are not going to check the other branches, right? So you always actually go to, okay, if this and this branch is going to give me the optimal answer, I'm not going to get anything better. So there is no need to check the rest of the branches, right? In a specific type of problems, we know that at each step of the search, what action is going to give me the optimal answer. And because of that, I would never do this, the complete search and check the other branches. So in each action, there is an optimal choice. This is a property for the problem. So that's the thing. The dynamic programming can be applied almost, anywhere that you are having a complete search, you can apply the dynamic programming. But the greedy algorithm will be applied only on a specific type of problems, those problems that has this property, that we can prove that at each step there is an optimal choice, that by following that I can actually get the optimal answer, so I don't need to do the complete search. So greedy algorithms are not applicable everywhere. Unlike dynamic programming, greedy algorithms are not applicable everywhere. Just specific problems can be solved using greedy algorithms. Even in the case of coin changing, we have seen the dynamic programming solution for the coin changing, right? And we know that not all the coin systems can be solved using greedy algorithm. The Canadian coin system, or for example American coin system, can be solved using greedy algorithm, and it actually ends up to the optimal answer. The whole idea, the whole strategy here is that always choose the largest coin, change with the largest coin, which is smaller than the amount that you are going to change, right? This is going to actually always end up to the optimal answer. But if I'm going to apply this strategy over a different set of over a different coin system, for example, assume that your coin system is something like, let me use a different color. The coin system that you have is for example 1, 5, 18 and 25. Okay, and you wanted to change an amount like 29. This is an example that we have seen in the dynamic programming actually case. you can see that if I'm going to choose the greedy strategy that tells me to use always the largest coin, this, so the greedy strategy is use the largest coin. The answer for this problem using the greedy strategy is going to be, so the largest coin, which is smaller than the amount I have, is 25. So you would use 25, and then you would use 4, 1. You can see that the rest, the amount that will remain is 4, which is smaller than 5. So you have to change it using the pennies. So this is going to be the answer that the greedy strategy is giving me. But the optimal answer is to use the coin 18, use 2 5s, and 1 penny. So you can see that this is going to give me just 4 coins, although the greedy strategy gives me an answer with 5 coins. So it's clear that the greedy strategy is not optimal in this coin system. So it actually just tells you that not always greedy algorithm doesn't always work. Dynamic programming always gives you the optimal answer because it does the complete search. So it makes greedy algorithm very tricky, where I can find a greedy algorithm, where I cannot find a greedy algorithm. The point is that you can actually have different greedy strategies, and if you wanted to prove the greedy strategy doesn't work, that's enough to just find a counterexample. For example, someone gave me this problem, and I wanted to actually just prove that the greedy strategy doesn't work in this problem. Just finding this example is enough. Just finding this example is enough to show that the greedy algorithm, the greedy strategy doesn't work. But if you want to claim the greedy strategy works and gives you the optimal answer, you have to prove it. For example, I'm claiming that the greedy strategy is going to work on this coin system, on the Canadian coin system. So I have to prove it. I'm going to actually show the complete proof. Over this lecture, I will show you different examples, and I try to actually discuss about some greedy strategies which are not optimal. So give you some example or some counterexample for them to just prove that they are not optimal, and give you some example that the greedy strategy works, gives you the optimal answer, and we have to actually prove it, that it is optimal. So let's just get back to this original problem that we have, the coin changing using the Canadian coin system. So if I wanted to write the problem in a more mathematical way, this is just like you have an X amount, and you wanted to actually rewrite this number using, in this form. That basically T is going to be the number of tunis that you need to change X, L is the number of loonies that you use to change X, Q is the number of quarters, D is the number of 10 cents, N is the number of nickels, P is the number of pennies that I used. So the thing is, because I have 1 penny, every amount of money that you have, you can change it. You can write it using a polynomial expression like this. right? And now the question is that I wanted to find all these numbers T, L, Q, D, N, and P so that the summation of these numbers is going to be minimized. This is the problem. I just rewrite the problem in a mathematical way. So this is just an example that show you that, for example, if I am going to change $4.87, the optimal strategy is telling you to use 2 twenties, and after that the remaining use the quarters, 3 quarters you can use, and then 1 dime, and then 2 pennies. So we wanted to prove that this greedy strategy that always takes the largest coin that you can use is going to give us the optimal answer. I have written it as a form of a theorem, and there are actually a couple of facts that we can let me actually it is just showing you that this greedy algorithm doesn't always work in all the different coin systems, and we have already seen some example of this one. So to actually discuss the proof, we can in fact find some properties about this coin system and the optimal and the greedy strategy that works on this. So assume that I know the optimal answer for changing X using this coin system. There are actually a couple of facts that I can draw. The first thing is that in the optimal solution that you have, the number of loonies that you will use is going to be less than 2. You cannot have 2 loonies in your optimal answer. And what is the reason? The reason is that if you are going to use 2 loonies, maybe it's not the best way to write it, so if you are going to use two loonies, I can simply just claim that instead of 2 loonies, you can use 1 toonie, right? And it's going to give you less number of coins. So this is the first fact, that the number of loonies in the optimal answer is definitely less than 2, less than or equal to 1. Okay, it's going to be either 0 or 1 loonie. I can draw some other facts as well, like the number of quarters is going to be less than 4, sorry. And again, the reason is that if you have 4 quarters, you can replace it with 1 loonie and use less number of coins. Another fact that I can draw is that the number of nickels, the number of 5 cents coins is going to be less than 2 again, because if you are going to have 2 5 cents, you can use a 1 10 cent instead of that, right? And in definitely the number of pennies are going to be less than 5, because if you have every 5 pennies can be replaced with just 1 coin, 1 5 cent, right? So these facts are clear, very you can actually just draw them very easily. There is one more fact that I wanted to claim, and this is about the number of 10 cents and the number of nickels. You can see that I draw actually some facts about the loonie, about the quarters, about the 5 cents, about the pennies. But what can I actually get about the number of dimes or 10 cents? There is one fact that I can claim, that the number of dimes plus the number of nickels, the 5 cents is going to be less than 2. You cannot have 3 of these 2 type of coin. And here the idea is that how can I actually prove it? What are the possibilities? Just assume that you can have, for example, 3 of these coins. If you have 3 of these coins, it means that there are different possibilities, right? For example, 3 10 cents, 3 dimes. If you are going to have 3 dimes, right, it means that it is going to be 30 cents, right? For the 30 cents, you can replace, instead of having 3 dimes, you can actually have 1.25. You can replace it with 1/4 and 1 5 cents, which is, you can see that the number of coins here is less than 3 dimes. So definitely it's not possible to have 3 dimes. What else I can actually say? If this number is greater than 2, so you might actually just say that, okay, 2 dime and 1 nickel. In that case, again, I'm actually just claiming that this is going to be 25, right? And instead of having these 3 coins, you can just replace it with 1 coin, 1/4, right? Again, less number of coins. So it's not possible to have this situation. You cannot have 2 dimes and 1 nickel. And there is no other possibilities if you're going to actually just say that 1 dime and 2 nickel. Already this is a contradiction with this fact that the number of dimes is going to be less than 2. You cannot have 2, the number of nickels is going to be less than 2. You cannot have 2 nickels because you can just replace this with 1 dime. Okay, so this is the next fact that we can actually just draw from this coin system. I have written all of these here, just a complete discussion. Okay, we have already found these properties about the optimal answer. These are the properties about the optimal answer. How I'm going to prove the greedy algorithms gives you the optimal answer? I'm going to show you that the greedy algorithm actually follows exactly the same properties, and in this way you can show that the greedy algorithm cannot give you any answer greater than the optimal answer. So now I want to write the complete proof. Assume I'm going to change the amount x, which is the amount x, which I can say that this is between some coins that I have in my system. I have written, actually, I have given some index to all the coins, k, and the ck shows the amount of that coin, and the amount that you are going to change is just between 2 of these coins. So if the amount is greater than $2, you can just simply assume, add one more index here. Just assume this is going to be 7, and the ck plus 1 is going to be infinity. So in this way, you are going to cover everything, okay? So every amount that you are going to change is going to be between 2 of these coins that I have, and you can see that I have actually, by adding one more row at the end, I am going to cover all the cases. So the greedy strategy claims that always go with the largest coin, which is smaller than or equal to the amount that you are going to change. So it tells you that always go with the coin k, or with the amount ck. I'm going to claim that any optimal solution also will take coin k for x. So if not, I'm going to actually just prove it using the contradiction. If you have to change the amount x and you are not going to take coin k, which the greedy will take, it means that you have to, instead of using the ck, you have to use some coins from c1 to ck minus 1, right? And if you think about the properties that I have I have actually written all those properties, all those facts that we draw in this table. you can see that if you don't take k for any of these, actually any of these rows, if you don't take the coin k, and you are going to change your amount using, instead of ck, you are going to use the coins from c1 to ck minus 1, you are going to need more number of coins than ones, right? So ck is going to be just one coin, right? If you are going to change it using the other coins, definitely you need more number of coins. These properties here shows you that whatever is ck, if you are going to use the smaller coins instead of that, you have to definitely use more number of coins. So it's not possible. Definitely the optimal answer, always take the coin k whenever it is actually changing this amount x. And this is enough to actually prove that always the greedy algorithm gives you the optimal answer, because you can just recursively have the same discussion over this amount x minus ck. We have already actually shown that the greedy algorithms for x will take the coin k, and the optimal also takes the coin k. And then you have you can actually have the same argument over x minus ck, and just repeat this until you reach to the amount 0. And so in this way, definitely the optimal answer and the greedy solution, both of them are going to be the same. We have already discussed that this algorithm, this greedy strategy to always takes the largest coin, is not going to work over all the coin changing system. Here I'm actually having some other example that try it. You can simply find a counter example that shows this coin system is this denomination system is not going to give you the optimal answer using greedy. This is interesting because this is actually the US postage. I actually saw this one in some other lectures. It was nice to check. Or for example, if you have your coin system in a like 7, 8, or 9, if you go with the greedy, in some cases, for example, if the amount that you are changing is 15, if you go with the greedy solution, greedy strategy, it actually end up to not having any answer. You can see that if I go with the greedy strategy, I would choose 9, and then the remaining cannot be changed using 7 and 8. Although I can find an answer, so 7 and 8 can actually change this amount. But the greedy strategy doesn't even give you an answer. Not only it can't find the optimal answer, it actually ends up to not able to solve the problem. So you might ask this question that, is it possible to check for each denomination? Is there any algorithm that you check each set of denominations and say that, okay, the greedy algorithm will work for this, it doesn't work for the other one? No, there is no algorithm, there is no formula, there is no way to, for any given set of denominations, you can check if the greedy strategy gives you the optimal answer for this set or no. You have to solve for any given set of denominations, you have to check the greedy strategy and see that if you can prove it is optimal, that's good. Otherwise, it means that it's not possible. The greedy strategy doesn't give you the optimal answer. But yet, I can actually give you this theorem. The theorem tells that if the denominations are in a specific form, that all of the coins that you have are going to be a power of some integer number c. For example, you have a set like 1, you can see that C0 means that whatever is C, you have 1. So In this way, you can definitely, whatever is the amount, you can always actually change it. 1, for example, 7, 49, something like that. This set, yes, the greedy strategy will give you the optimal answer for this set. Or for example, something like 1, 3, 9, 27. The greedy strategy will give you the optimal answer on this set. You can see that all of these sets are in this specific form, that the coins are all powers of the same integer, positive integer number. This theorem, we can prove it, actually. We can prove that the greedy strategy gives you the optimal answer if the coins are in this specific form. But this is not the if and only if case. You can see that, for example, the Canadian coin system doesn't actually follow this format, but still the greedy strategy gives you the optimal answer. If your coin system, if your denomination set is in this form, definitely the greedy strategy is optimal for that. But there are some other sets that the greedy strategy gives you the optimal answer, but they are not in this specific form. That's why I told you that there is no algorithm to check if for a given set of denominations the greedy strategy is optimal or no. So for any given, you have to actually just prove it. Try to actually prove this theorem. This is going to be a very good exercise. I'll try to post the solution, post the proof for this theorem. So the next problem that we are going to discuss is the knapsack problem. Remember, we have discussed knapsack in our discussion about the dynamic programming as well. So this is exactly this problem that I have written here is exactly the problem that we solved in the dynamic programming discussion. Let's just repeat the problem. The problem was that you have an object, and for each object you had some value and some weight associated to that object. And we have, just assume that we have a knapsack with a specific capacity. You cannot carry more than that capacity, that weight on that knapsack. And the problem is that we wanted to choose the set of objects that gives us the maximum value, while the weight, the summation of weight is going to be less than the amount that we can, less than or equal the amount that we can carry. So the knapsack problem, which is 0-1, the 0-1 knapsack problem, that you either choose the object or don't choose it, we solved it using dynamic programming. And the thing is, you cannot solve this problem using the greedy strategy. There is no optimal greedy strategy to solve this problem. I'm going to show you a couple of greedy strategies and see that if they are going to give us the optimal answer or no. But let's just actually stick to this example and see that what is the optimal answer for this example, this example that I draw here for you. The optimal answer in this case, you can see that I have actually put all the items, the value for each item, and the weight for each item. If the given weight, the total weight that we have is 100, the optimal answer, I know that the optimal answer, if you actually do a search over the objects, you will see that the optimal answer that we can get is by choosing the object 1, object 2, object 5, and object 6, that in total it's going to give me the value 290, and the weight is going to be less than or equal to 100. The weight is going to be 90. So now let's look at a couple of greedy strategies. Someone might actually claim that to solve this problem, instead of do the complete search, always choose the most valuable item. This greedy strategy kind of is is tempting, right? Because it's actually telling you that take that object that has the highest value. You're going to maximize the value. So you might actually just say that, okay, here the intuition is that we wanted to take the one that has the highest value. The other strategy is that always choose the heaviest item first. This is kind of silly, but anyway, I wrote it here for you. The next strategy is that always choose the lightest item. There is an intuition for this one as well, because if you use the lightest item, it's just like you are leaving more a space for the choosing the rest of the items. This is kind of intuitive, but here you can see that it doesn't actually consider the value of those objects. Maybe an object is very light, but the value of that is also very light. So we will see some counterexample for all of them. And the last strategy is that choose an item, always choose the item with the maximum ratio of the value per weight. So you can see that among all of these 4 strategies, the last one is more intuitive. And it actually makes more sense because it considered both value and weight. It's trying to take the item that has the higher value, considering the weight of that. So this ratio value per weight. Let's just actually try to run all these greedy strategies over the example that we had and see that what they are going to give me as the final answer. If I go with the first strategy, it tells me that always takes the one that has the highest value, right? The highest value for me is 85, right? So it's telling me that to take 3 first, and then you will actually need to use 70, so you end up with 30, for example, kilograms. And after this, what you can take, the next most valuable item, which is still the weight of that is going to be less than 30, is object 1, right? And so I'm going to take 3, I'm going to take 1, and it remains, we are going to have 5 more kilograms to fill. And the only object that I can take is going to be 6. So 3, 1, and 6. The total value that I can get from this is going to be, I think, 230. This is going to give me the maximum value that I can get, right? The next strategy tells me to always take the heaviest one. Based on the weight, the heaviest one is going to be, again, 3, and then after that you will have only 30 kilograms. Then you cannot take 2, you can take 1. It is going to be the next heaviest item, and then you will take 6. This is going to be exactly the same. Actually, this is just in this example, they happen to give me the same answer, but it's not always the case. But anyway, the next strategy is to always use with the lightest one. The lightest one based on the weight is going to be 6, right? And then after that, you are going to choose 4. And then after that, you are going to choose 5. Still you are going to have 60, so still you can take 1, right? You can't take 2 anymore, and you can take anything else. So the optimal answer here is going to be 6, 4, 5, and 1, which the value here is going to be 260. Anyway, so far we have seen that none of this is going to give me the optimal answer, because I already know that the optimal answer in this example is 290. And let's check the last strategy. The last strategy is about taking the item with the largest value per weight ratio. So it will be take 6 first, then take 5, then take 1, then you can take 4, this one, and then you can't take anything else. So again 6, 5, 1 and 4, and the total value is 260. So none of these strategies give me the optimal answer, and none of them is optimal, in fact, for the knapsack, 0-1 knapsack, that you can either take the item or just leave it. So there is no greedy algorithm that works in this problem. I'm going to actually just leave this problem. We have already solved it using dynamic programming. But I'm going to change the problem and give you the simpler form of the problem, that we have loosened that restriction over the 0-1. And so this problem is called fractional knapsack. It means that from each object, instead of taking the whole object, either actually take it or not take it 0-1, you can take just a portion of it. You can take a fraction of that item, something between 0 and 1. You can take just, you can just leave it, or you can take, for example, 10% of it, 5%, 13%, whatever fraction of the object you can take. So this problem is inherently completely different than the other problem. And I'm going to claim that for this problem, there is a greedy strategy that gives you the optimal answer. And that greedy strategy is, in fact, the last strategy that we discussed. Always choose the item with the maximum ratio of value per weight. I'm going to claim that this is going to give you the optimal answer. Let's just apply it over this example. If I'm going to apply this strategy over this example, it tells you to take 6, and you can take everything from 6, right? Whenever you can't take the full amount of an item, just take that portion that you can take. It actually allows you, right? So every time we just take, try to take some amount from the object that has this highest value per weight ratio. So we can take the full object 6, and then the next highest value per weight ratio is 5. I can't take all of it. I still have enough capacity. Then I can take the full amount of the object 1. Then I can then the next object is 4. I can take the full amount of 4. What will remain in this situation after you took 6, 5, 1 and 4? Then you will end up with just 35, weight equal to 35. I cannot take the full amount of the second object, but instead of actually taking all of it, I'm going to just take as much as I can. I can take 35 kilograms, so from the 40 kilograms, the total object, I'm going to just take 35 kilograms of that, which is going, if you actually multiply it by the value, this is going to give you 61.25. So in total, so a portion of, it's just like 65 divided by 40 from the object 2. It is not actually the multiplication from the object to. Okay, in total it's going to give me this amount, and this is the optimal. So if I'm claiming this is going to give me the optimal answer, this is strategy, I have to prove it. How I'm going to prove this, prove that the greedy strategy, this greedy strategy is going to give me the optimal answer. Let's just assume that there is an optimal answer. I wanted to actually show you that the greedy solution is not going to give me anything different than the optimal. So at first I'm assuming that the optimal solution is, let's call it S, okay? There is an optimal solution S, and there is I'm going to compare it with the solution that the greedy strategy is going to give me. I'm calling the solution from the greedy strategy to be G. Okay, so let's just sort all the objects that we have and say that, for example, in the optimal answer, how much of the, for example, the object 1 I'm taking, how much from the object 2, how much from the object 3. I can actually just write the solution in that way, right? And also, let's just assume that I have sorted all the objects based on the ratio value per weight. Okay, so it's just like from the object 1, how much in this way. So objects and object 1, object 2. I'm actually just trying to give you some organization, some structure over the solution. Object 1, object 2, object 3, until object, for example, N. Okay, and in S, it actually just, it tells me that how much from object 1 you have taken. Okay, let's just call this one S1. How much from object 2 you are taken in the optimal answer. Let's just call it S2, S3, until Sn. And I can actually write down the same thing for G as well, that how much from object 1 I'm taking in the greedy, how much from object 2, object 3, until the last object. Okay, and I'm sorting all these objects based on the value per, so the first object is going to have the highest value per weight ratio. I've just sorted these objects in the decreasing order based on the value per weight. Okay, if you compare these amounts, S1 and G1, S2 and G2, if we are saying that the optimal answer is different from the greedy solution, from the solution that the greedy strategy gave me, it means that there should be some differences between these amounts, right? The S1 G1, or there is some difference between S2 G2, somewhere there should be some differences. Okay, so let's just assume that the earliest difference between the solution in the optimal solution and the greedy solution is happening somewhere like, for example, SK and GK. K can be 1, it can be N. It doesn't really matter. I just write it as SK and GK because I just wanted to give you a general discussion. That there is difference between the optimal answer and the greedy answer, and tells you that GK is not equal to SK. The amount from object K that you are taking is different in the optimal answer and in the greedy answer. I'm going to claim that definitely if they are different, GK
is going to be greater than sk if they are different. And the reason for this claim is that the greedy solution, the greedy strategy always tells you to take as much as you can from each object with the highest ratio, the value per weight ratio. So if there is going to be any difference between JK and SK, definitely JK is going to be greater than SK, right? And if it is the case, this is contradiction with the being the optimal answer. Because if you are taking less amount of object K, you are taking more from some other objects here, right? You are taking more from some other objects here. But if you are replacing, definitely all those objects that you are taking are going to have less value per weight ratio, right? So if instead of SK, you take GK, you are using the same amount of weight and you are taking more value. So it's going to be actually a contradiction. You can replace wherever you have a difference between SK and GK, you can replace, if I actually just use a different color, probably it was better to use a different color for these solutions. I can just started changing the optimal answer, and instead of SK amount, let's just take GK amount, and the answer is going to be better. Okay, it definitely it cannot be worse because the value per weight ratio are going to be higher for this amount. You are going to take more value if you take more amount from the object K. So that's it. I'm done with the proving that the greedy solution definitely gives you the optimal answer. I have written the complete proof here. I mean, it's kind of actually just written, but this was the explanation of that. So I'm going to just leave this written part for you to read it and see that how we are going to write it on paper if you are going to write a proof. But this was the explanation. The next problem that I'm going to discuss is interval scheduling. Again, we have seen a version of this problem when we discussed about dynamic programming. Now you can see that why I'm saying there is a close relationship between dynamic programming and greedy algorithms. If you can't find a dynamic programming algorithm for a problem, then after that you can try to actually just see that is it possible to find a greedy solution for that or no. In all of those examples that I gave you in dynamic programming case, it was not possible to find a greedy optimal answer. But if we change the problems like in the knapsack, I loosen the constraint over the object, so you can take a fraction of an object. And here, the interval scheduling problem that we have, again, is going to be, a less restricted version of the one that we discussed in dynamic programming. Let's just get back to the problem. The problem is telling me that I have n jobs, n activities, and I'm going to just assume that you have, for example, one room or you have one machine and you wanted to take as much as job as possible to run on that machine, or you want to take as many as activities that can be done in that, for example, room. Okay, the difference between this problem and the previous one is that there is no cost or weight associated to the jobs, to the activities. All of them are going to pay the same. So it doesn't matter if you are taking the one that takes longer or you are taking one that takes a shorter time. Okay, so it makes it a simpler version of the previous problem. And for all of the jobs and activities, there will be some interval that tells me that the job or activity needs to be done in starting from S1, for example, to F1, starting from S2 to F2. There is going to be an interval associated to each job. And of course, we wanted to make sure that the set of activities or jobs that we choose, there is no conflict between them. All of them should be compatible with each other. So let me give you an example. I have 11 jobs and all the starting and finish time for all of them are written here. What is the optimal answer for this problem? Think about it. I'm not going to actually give the optimal answer on this one now. Let's just think about the greedy strategies that might come to mind. I have written actually a couple of them here. There are more. This problem is a very famous problem to discuss in the greedy algorithm part, and you can write many different strategies for this problem. I have just written 4 of them here for you. The first strategy is telling that always select the activity that starts earliest. So it's just like you sort all the activities based on the starting time and choose the one that starts earlier. Then the next job that starts earlier and there is no conflict with the previous one. So always the choice is that choose the next job which starts earlier, earliest, and there is no conflict between this one and the previous ones that you have already chosen. This is one strategy. The next strategy is that always select the activity that ends earliest. So this time we have sorted all the jobs based on the finish time, and it's telling me to choose the one that finish earliest. Then the next one always, always go with this strategy, and again, always choose the one based on this strategy which there is no conflict with that one and the previous chosen objects. The next strategy is talking about the length of the the time that takes for each job or activity. Select the activity that has the shortest interval. It's very intuitive, right? Because if you are taking less amount of time, probably you are going to leave more time for the choosing the other activities or jobs, right? And the next strategy is that select the activity with the smallest number of conflict. This one is also very intuitive, that I'm going to actually just discuss about all of them and see that which one is going to be optimal. If something is not optimal, that's enough to find a counterexample for that. So let's first look at the first strategy that was telling you to sort all the activities or all the jobs and takes the one that starts earliest. If you think about it a little bit, you will see that I can easily find a counterexample for this case. The counterexample, one counterexample is this, that, for example, in this case, the job 1 started earliest among all of them, right? But if you take this one, you cannot take any other job, and it will be just one job, although you could take all other 4 jobs and there was no conflict between them. So of course this is not going to give me the optimal answer. The next strategy that I'm going to check is it's telling me to always take the activity with the shortest interval. The intuition here is that when you are going to choose the shortest interval, you are allowing more time for choosing the rest of the objects, right? But for this one also I can't find a counterexample. Look at this. Job 2 has the shortest length, but if you take job 2, because it has conflict with the 2 other jobs, you cannot take anything else. Although you could choose one and 3, there was no conflict between them, and this way you could choose 2 instead of 1. So that's enough to prove this is not going to be the optimal strategy. And the next strategy is that always takes the job, the activity that has the smallest number of conflicts. Also, for this one, there is an intuition that if you are taking the job with the smallest number of conflicts, again, you are putting less constraint over the rest of the activities to take, right? Think about how we can find a counterexample for this one as well, because it's not going to be optimal, actually. This is very interesting. I'm going to give you an example, a counterexample for this. It's kind of tricky to find this counterexample, but after you play with these strategies a little bit, you will get used to it and see that how to find a counterexample. This counterexample, it actually shows you that the greedy strategy will started. Okay, before applying the greedy strategy, let's calculate the number of conflicts for all these jobs. Okay, this job is going to have 3 conflicts. This one is going to have 4 conflicts, 4 conflicts, 4 conflicts. This one is going to have 3 here, 1 here, 4 conflicts. This one is going to have 4 conflicts. This one is going to have 2 conflicts. Again, this one is going to have 4 conflicts, 4, 4, and this one has 3 conflicts. So based on, after I have calculated the conflicts for all the jobs, now I can apply the strategy. It tells me to start it from the smallest number of conflicts. So this is going to take this job, right? After that, it is going to choose this one, then it is going to choose this one. And you cannot take anything else because all other jobs are going to have conflict with this. But what is the optimal answer? The optimal answer is taking this one, this one, this one, and this one. You can see that the optimal answer is 4 activities, but the greedy strategy gives you 3. So this counterexample is enough to show this is not optimal. And the last greedy strategy was telling you to sort the jobs based on the finish time and always takes the one that finishes or ends earliest. Okay, let me just give you this thing that try to find a counterexample for this, and you will see that it's not possible to find a counterexample because this is the optimal greedy strategy. It's going to give you the optimal answer. I'm going to apply it over the first example that we had, and then I'm going to show you the proof that this is really going to give me the optimal. I have to prove it. So if we look at this example, as you can see, I have already sorted all the jobs based on the finish time and give them the names. So the first job that actually finished earliest is going to be job 1, right? If you look at the finish time, you can see that job 1 is the one. I have already sorted them, so job 1 is going to give me the earliest finish time. Then job 2 is the next earliest finish time, but I can't take it because there is conflict between 1 and 2. The next earliest finish is 3. Again, I can't take it. There is conflict. The next earliest finish is 4. There is no conflict. I'm going to take that. The next earliest time is 5. There is conflict. I can't take it. 6. There is conflict. 7, there is conflict. The next job that I can take is 8, which has the earliest finish time, and there is no conflict between that and the previous jobs. After 8, I can take 9, I can take 10, and then I can take 11. 4 jobs. And there is no other solution with more number of jobs. This solution is optimal. So the whole algorithm, before actually showing the proof of the optimality of that strategy, that greedy strategy, is that what is the algorithm? The algorithm using this strategy will be first sort the activities based on the finish time, and then start from the first job, takes that, and then always try to just find the next job that there is no conflict between that one and the previous jobs that you have already taken. This part is going to take O of n log n. If you have n jobs and you are going to sort it based on the finish time, the time complexity is going to be O of n, right? And this part, I can simply just write this one in O of n. I just need to go through all the jobs from the first one, and the next job you can simply just check the conflict between this one and the previous one. If there is conflict, you don't actually take that. The next job, you just need to check it with the previous taken job. And that's it. That's, the constant amount of work to check the conflict for each job, and this can be done in O of n. Try to write the code for this example, this problem, and just as an exercise, this is going to be a nice, especially writing down this part in an optimal way. This is going to be nice. So now let's actually go back to the proof. We are going to prove that this greedy strategy is going to be optimal. This is going to give me the optimal answer. The idea of the proof actually comes from this idea that if you always take the job that finish earliest, it's just like you are leaving more time for the rest of the jobs to be chosen. This is the intuition. This is the idea behind that. That by taking the job that finish earliest, you are leaving more time for the rest of the jobs to be taken. And it's just like you are thinking about the time in a linear format, right? You started from the first, and you choose a job. If you choose the one that finish earliest, you are going to leave more time for the rest. But how can I actually prove this? I'm going to prove it in this way, that by comparing something kind of similar to the proof that we discussed for the knapsack, the fractional knapsack, I'm going to compare the solution that the greedy algorithm, the greedy strategy gives me, and the solution that an optimal solution. And I'm going to claim that the greedy algorithm is also optimal. You can change the optimal answer and reach to the greedy answer without without making the number of jobs that you have taken less, without making it worse. So here again, let's just assume that I have an optimal answer, and I'm going to compare it with the greedy answer. I'm going to use different colors here. The optimal answer, this is actually the optimal answer. This is the answer that the greedy algorithm gave me. I'm going to write down the optimal answer in green. Let's just write it in this way, based on the starting, the intervals.
starting from the first one, then the second one. These indexes is just actually telling you that this is the index in the optimal. JL and F of JL. Okay, and this is going to be the greedy solution. Assume that I have sorted the jobs based on, it doesn't matter, both optimal and the greedy, I have sorted them based on their finish time. No, this is going. I don't know. The claim here is that L is going to be greater than or equal to K, because this is going to be optimal, right? So I don't know if K is equal to L or not. I'm going to prove you that K is equal to L. How I'm going to prove it? The thing is, just assume all of these, it doesn't matter, in both the optimal and also greedy, I have sorted the jobs based on finish time. Okay, so one thing that I know is that the finish time in the greedy answer, this is greedy and this is the optimal answer. I don't know if it's clear that this is optimal. Let's just use S, maybe it's more like the previous notation. This is the optimal answer and this is the greedy answer. I'm going to claim that the finish time of the first job is definitely going to be less than or equal to the finish time of the first job in the optimal solution. I can claim that, right? By comparing these two, I can claim that the finish time of the first job in greedy solution is less than the finish time in the optimal. Because the greedy strategy was always to take the job with the earliest finish time. Maybe these two jobs are going to have the same finish time, right? That's why I have actually written it as less than or equal. And one more thing that I know is that this job and the next job, there is no conflict between them. So of course the finish time of the first job in the optimal answer is going to be less than the starting time of the next job, right? There is no conflict. Okay, so instead of, I can actually claim that instead of this job, if they are different, if this job in the optimal answer is different than the job that the greedy solution taken are different, I can claim that without changing, without anything, without any conflict, I can just replace this solution, this job with this job. It means that I am going to, instead of using this job,
I'm going to use exactly the same first job that the greedy algorithm gave me. So it's just I have replaced the first job in the optimal answer with the first job of the greedy. And there will be no conflict, right? I didn't actually make the optimal answer worse. I just replaced that. I'm going to have exactly the same, use a different color, exactly the same discussion for the second jobs. And gradually just replace all the jobs in the optimal answer with the one from the greedy solution. Maybe the optimal answer is different, but I'm trying to tell you that I can just change the optimal answer to the greedy. All of the choices can be changed to the greedy choices, and you are not making the solution worse. You are not losing anything in your optimal answer. So that's enough to prove that the greedy strategy is going to give you the optimal answer. It's going to give you the number of jobs equal to the any optimal answer that you can find. So this was the explanation, and I have written, how to write it down on paper. I have written actually the complete proof here. Okay, so we are done with this interval scheduling.